Hello, good morning, good afternoon, and good night to all the attendees across the world. My name is Murat Yokus. I'm a postdoctoral researcher at North Carolina State University in the United States. Today, I'm happy to share with you our preliminary results towards developing a continuous and variable sweat rate sensor. I'm going to start my talk with a brief discussion of eccrine sweat glands, dehydration-related medical conditions, and an overview of sweat loss and sweat rate measurement techniques. Then I will introduce the variable sweat sensor we developed, which will be followed by benchtop microfluidic and electrical characterization results. And finally, I will end my talk with conclusion and future work. So let's get started. As we all know, sweating plays an important role in regulating body temperature. As the body temperature rises, the eccrine sweat glands in the dermis layer of the skin excrete water through the pores. So the resting sweat on the skin surface then evaporates and cools off the body. The sweat collected on the skin surface is composed of mostly water and electrolytes, in addition to other metabolites, hormones, and proteins. And considering the quantity and the density of the sweat glands, sweating under extreme conditions, such as exercise or heat, can be as high as 16 liters, which can actually disturb the human homeostasis, impairs the circulation, and impedes the heat dissipation. Therefore, sweat rate measurement is crucial for replenishment of water and electrolyte loss. Excessive sweat loss due to exercise or heat can lead to various medical conditions, which can range from dehydration, hypernatremia, heat stroke, muscle cramps, to decline in mental and cognitive performance. Therefore, in the long run, actually, tracking sweat rates enables users or athletes to achieve their optimum performance, and also it eliminates the potential health complications related to dehydration. Traditional sweat loss measurements involve whole body washdown technique, use of absorbent patches, and microduct for regional sweat loss measurements. Even though these measurements have been quite helpful in the past, they involve complicated steps, require trained personnel, and they're also sensitive to fluid evaporation and contamination from skin surface. On the other hand, recently, skin-borne sweat rate microfluidic devices have been developed, mostly relying on volumetric expansion of polymers, such as hydrogels, and filling of microfabricated PDMS microfluidic channels. Epithermal sweat rate sensors were also integrated with electronics. They are mostly relying on impedance sensing and differential water vapor sensing on the skin surface. Some of the challenges still remain in this field, such as variability, miniaturization of the overall system, electronics integration with the microfluidic platforms, and continuous sweat rate assessment without the need of user interference. To overcome some of these challenges, we have developed a wearable flexible sweat rate sensor, which consists of a pair of screen-printed interdigitated electrodes shown with black color on polyimide substrate, and a paper-based microfluidic channel for fluid transport from inlet to the outlet, and also a polyurethane encapsulation layer to minimize the sweat evaporation over time. So compared to its polymer-based microfabricated counterparts, this technique is low cost, easy to fabricate, and also it enables continuous wicking of fluid without formation of air bubbles in the microfluidic channel, which is actually a common problem in PDMS-based microfluidic channels. So overall, the proposed system here, the sensor here, is flexible, and also it enables continuous quantification of sweat loss over time. Our initial measurements were on the microfluidic characterization of the sensor to determine the total fluid volume and the filling time of the microfluidic channel. For this purpose, we broadcasted 200 microliter of phosphide buffered solution to the inlet of the microfluidic channel, and then a digital camera was set up to record the fluid flow in the channel over time. At the same time, we simultaneously measure the admittance between the interdigitated electrodes using a benchtop potentiostat, which will be discussed in the following slides. So, as you can see from the graph on the left, the fluid velocity in the channel decreases over time due to a decrease in the capillary pressure in the porous paper medium, according to Doherty's law. Also, the increase in the distance taken by the fluid front end slows down over time, which can be explained by the Lucas-Washburn equation. So the graph at the middle shows the total volume of the microfluidic channel. The channel can hold up to 82 microliters of water, which can be further modified by adjusting the dimensions of the microfluidic channel. And finally, the graph on the right shows the fluid volume between each electrode pairs for different channel dimensions. For example, for 3 millimeter paper width, the water volume between the electrode pairs was about 15 microliter, which will be useful for sweat rate calculation in my following slides. The microfluidic characterization of the sensors was followed by the electrical characterization to determine the time point at which the collected fluid crosses the interdigitated electrodes. The figures at the top show the admittance increase as the fluid fills the microfluidic channel over time. And the figures on the second row are the time derivation of the data on the top graphs. So if we can focus on these graphs on the right, we can have two main conclusions. First, increase in the admittance was much higher for the wider paper channels. On the top row, for the first and second graph, if you look at the other graphs, we can see that increase in the admittance was much smaller. Second conclusion is the large admittance changes can be translated into detectable spikes compared to the background noise after taking the derivation of the admittance data, which was useful for determining the time intervals between the subsequent peaks. So far in the previous slides, we have determined the fluid volume between the interdigitated electrodes, and also we measured the time intervals between the admittance peaks. So if we divide these two values, we can easily calculate the flow rate in the paper-based microfluidic channel. As we can see from the graph on the right, the calculated flow rate starts from about 15 microliter per minute and it decreases over time. So if we do some back of the envelope calculations and assume the sweat rate per gland as 20 and sweat gland density as 150, with the inlet area of 0.2 centimeters square, the perfused sweat rate on the skin surface on the wrist, for example, would be 0.6 microliter per minute, which can be easily detected by our sensor. To conclude, overall, we have demonstrated an inexpensive fabrication technique involving screen printing of carbon inks on flexible films and integrating it with paper-based microfluidic channels and polyurethane-based encapsulation layers. Then we performed microfluidic and electrical characterizations for continuous sweat rate assessment. Our future work will include investigation of the relationship between the perfused sweat on the skin surface and also flow rate in the microfluidic channel. And also the future work will include in vitro characterization of the sensors with a custom designed PCB, which is shown on the right. Finally, future work will involve on-body sweat assessment in multiple human subjects. With that, I'd like to thank Dr. Daniele and Dr. Bozkurt for their help and guidance throughout this study. I'd like to thank my collaborators, Talha and Matt, and also all Biointerface Lab members. Lastly, I want to highlight the funding. So the funding for this study comes from Assist Engineering Research Center at NC State University. This ends my presentation, and I'm happy to answer any questions you may have. Thanks for listening.